All right, so in this lesson, we're going to do a little bit of investigation, and we're going to hopefully get some hints and be able to decipher some information about our system of equations without having to always do all of the work. Mainly, our goal is to be able to look at a system of equations and know whether it can even be solved, because sometimes it can be, sometimes it kind of can be, and sometimes it can't be at all. So let's start off with a bit of investigation via graphing. So we're gonna do something that we've already done before. Everybody's comfortable with this. We're going to graph these 6 equations. They're in 3 groups of 2, and we're going to graph using the slope and y-intercept method. So that means that we need to put each equation into standard form, and then we can just read off the slope and the y-intercept from there. So for example, in the first set of equations, pardon me, we have y is equal to 2x plus 1. Well, that's already in standard form. So we can get the slope. Well, that's the slope. There's the m there. So that's a 2. It's rise over run. So we'll put the 2 over 1 here. And our b value, that's the 1. So the y-intercept is located at 0, 1. Great. All right, let's look at the next one. So now, again, we have a slope of 2 over 1. Okay. And this time our b is negative 2. So that means our y-intercept is located at 0, negative 2. Let's go take a look at the next one. I'm going to kind of bounce back and forth a little bit here while we do this. So the next set of equations we have, well, this one's not in standard form, so we got to rearrange it a little bit. So when we rearrange this, when we isolate y onto the other side, and we bring the 1 to the opposite side, we end up with x minus 1 is equal to y, but let's reverse that just so it's a little bit clearer for all of us to read. So that's y is equal to x minus 1. Now we can see something that we're more comfortable with. Now looking at this, our m is just a 1, so that's a 1 over 1. And our b is a negative 1, so that means our y-intercept is at 0, negative 1. Now, before I go any further into this one, some of you may have a version of the course pack that has an error on this question, and your question may say 3x plus y is equal to 6. This should definitely be a 9, so please correct it on your course pack if that is the case. Anyways, so we have to rearrange this one again. This one is not in nice standard form, so let's kind of move this over here. So we're going to bring the y, we'll bring the 3x over to the other side since the y is positive here. So we have y is equal to negative 3x plus 9. So there's our slope. Our slope is going to be negative 3. Put the run over there of 1. And the y-intercept is just 0, 9 because the b value is a 9. Now we have our last one here. We have to rearrange these. So before we scroll down and put them in the right spot, we'll rearrange them first of all. Now this one, it's not the prettiest one in the world. It's going to take a little bit of work, but we can still do it. So first off, we want to get the y all on its own. So we're going to leave the negative 10y on the left, and we're going to bring the 4x over to the other side. So that means that we have negative 10y is equal to negative 4x plus 20. Now we got to divide everything by negative 10 to get the y on its own. So we have y and negative 4 divided by negative 10. That's going to be 2 over 5. We can't really reduce that any further without getting into decimals, and we don't want to do that. And then we have 20 divided by negative 10, so this is going to become a negative 2. Okay. So in this case, we have an m of 2 over 5, and we have a b of negative 2. Let's check the next equation. So in this case, we have negative 5y, and that's going to be equal to, we got to bring the 2x over to the other side, so minus 2x plus 10. Now we got to divide both sides by negative 5. So we have y is equal to, 2 over 5x. Well, that's interesting. They both have the exact same slope, 2 over 5. And now we're going to do 10 divided by negative 5, so that's minus 2. Oh, they also both have the same y-intercept. So let's scroll down here and put that down here. So they both had, where'd my pen go? Well, they both had a slope of 2 over 5. And they both had a y-intercept of 0, negative 2. All right, so now that we have all of our data for all 6 equations, we don't even need to look at the equations anymore. Now we just need to graph and see what we can see. So for the first one, we see that it has a y-intercept of 0, 1. All right, so there is the y-intercept. Alrighty. And it's got a slope of 2 over 1. So up 2 over 1. Up 2 over 1. Up 2 over 1. Up. No, can't go anymore. And we'll go 1 this way. Alrighty. So see how well I can draw a line here freehand. You guys have seen my handwriting, so we'll see how this goes. You know what? Could be worse. So this is equation 1. All right, equation number 2. This one starts at -2, but it has a slope. Oh, they have the same slope. Up 2 over 1. Up 2 over 1. Up 2 over 1. Up 2 over 1. Let's see how I do here. Well, that is interesting. So what kind of information can we pull out of this? Well, first of all, are they ever going to intersect? They're not. They're parallel lines, which means they're never going to point into each other in any direction. They're always going to move alongside one another. So that's a pretty interesting point to make. So what that means is that these lines, they have the same slope, right? So that makes sense. And that's why they're never going to touch. But they also have different y-intercepts. They have different y-intercepts. So what we can say is that because they are parallel, they have the exact same slope, they're parallel lines, what that means is that it's impossible for them to touch. So there are no solutions. Because remember, a solution to a system of equations is a point of intersection. There's no such thing as a point of intersection. So we can say that there are no solutions. The lines are parallel and distinct. Distinct means that they are not the same lines. Okay? Not the same line. This is important because if they were the same line, they'd still be parallel, but they'd definitely be touching. All right. So that's a pretty interesting one. So let's go down to the next one here. So the next one, it's at 0, -1. And it has a slope of 1 over 1. So this is like a perfect 45-degree angle. It's just going to keep going up on the points. Nice and simple. I've definitely drawn better lines, but we'll see how that goes. The next one is all the way up at 0, 9. It don't even have the point there, so we're going to have to kind of wing it here. And this one has a slope of -3 over 1. So let's see how this goes. 1, 2, 3 over 1 right here. 1, 2, 3 over 1 right here. 1, 2, 3 over 1 right here. And we'll do one more. 1, 2, 3 over 1. So now I got to try and draw a slope going the opposite direction. This is substantially more difficult. All right, so we got equation 1 and we got equation 2 here. Now in this case, they both have different slopes and they both have different points of intersection. So because they have different slopes, they absolutely will cross at some point. So the lines have different slopes. They have different slopes. So that means that there is going to be exactly one solution. Now I'm going to add a little bit more to this. So these lines have a different slope. Their y-intercept, you know what? That y-intercept could either be the same or it can be different. It doesn't make a difference in this case. Because they have different slopes, it just doesn't matter. So in this case, I'm going to say the lines have different slopes, and in brackets, I'm going to say y-intercept can be the same or different. There we go. Handwriting perfection. Alrighty. Let's go down to the last little bit here. Now this was the weird one. These ones both had the exact same point of intersection. Okay, 0, -2. And the other one's 0, -2. I'll just draw it darker. Yay. Now it's got a run, or a slope of 2 up 2 over 5. 1, 2, 3, 4, 5, right there. Now we can't go all the way over in this one, so let's go down the opposite direction. So down 2 and left 5. 1, 2, 3, 4, 5, right here. Now we're going to, well, that was pretty terrible. Is there an undo? We're just going to erase that one and try again, because that was pretty awful. Let's see. Down 2, over 5. 1, 2, 3, 4, and 5. That's better. Okay, here we go. We're going to try our best and do this line. All right, winner, winner, chicken dinner. We got that one. Awesome. So you know what the weird thing is? This is both equation 1 and equation 2. They're literally sitting on top of each other. So these lines have the same slope. They also have the same y-intercept. You know why? Because they are the same line. If we go up to those equations again, whoa, I went a little farther. And there we are. If we go up to those equations, the equations broke down into the exact same equation. These things are equivalent. If I take this bottom one and just multiply it by 2, I get the top equation. So they are the same line. So when I'm writing down my notes here, I can say that these lines, that there are actually infinite solutions. So that means every single point they're touching. So they're all points of intersection. The entire line is full of points of intersections. So we could say that there are infinite solutions, and the lines are, there's a special term for this, coincident. Coincident. That's a funny big word. You can use it. There's a lot of synonyms for this word. You could use equivalent. Or if you really want to keep it simple, you could just say they're the same line. All three of these things mean the exact same thing. Coincident is the correct mathematical term that we use, though. All right. So what we can see from this then is if we can determine the slope and the y-intercept just from those two pieces of information, just by looking at the numbers, without even graphing it, just by looking at the numbers, we can determine whether there is one solution, no solutions, or infinite solutions. We don't even have to do the work. That's good news. That could save us some time. Let's go down to the next page and put this to work. So what would happen if we tried to solve a linear system using substitution that had no solution or infinite solutions? What would actually happen to that system of equations? So in the last lesson, we learned how to use substitution to solve a system. Let's see what happens if we try to do that on a set of equations that doesn't have data that is nice. That's going to end up with either no solution or infinite solutions. So let's give this a go. So the top one here, I don't know which is which yet. I'm lying. I actually know, but for the purpose of this lesson. All right. So step number 1, we got to label these equations. So this is going to be equation number 1. This one is going to be equation number 2. First thing we have to do is we have to isolate. So we can choose one of the equations to isolate. Obviously, equation number 2 is nice and simple because x doesn't have any coefficients at all. So we're just going to shove that 2y to the other side. So you are going to become equation number 3. And you're going to say x is equal to 5 minus 2y. Okay, now that we have this value, we can substitute it into the opposite equation. So we're going to say sub equation 3 into equation 1, and our goal is to find y. Okay, so wherever we see an x, we have to put 5 minus 2y. So 2 times 5 minus 2y plus 4y is equal to 8. Now we just got to do the work. 2 times 5, we got to distribute here. 2 times 5, well, that's 10. 2 times negative 2, that's going to be minus 4y plus 4y is equal to 8. Uh-oh. So we have 10 minus 4y plus 4y. Those both go away. And on the other hand side, we have 8. 10 equals 8. That is not possible. So that is what happens. That is a problem. So what does this mean? Well, I'm going to use a since statement. Remember, since just looks like an upside down therefore. It's basically so we can give an explanation of things. So since this is an impossible situation, this is an impossible situation, that means that there are no solutions. It's impossible. Therefore, no solution. And since there's no solution, that means we could say, because we know that when there is no solution, the lines must be parallel and they must be distinct. The lines are parallel. If we put the time in to actually graph them, we'd find this information, but we don't need to. There we go. So that's what it looks like when there are no solutions. You get an impossible situation when you substitute your values back in. All right, let's try another one. This time, we're going to solve by substitution again. Oh, good. We already have one that's nicely isolated for us. There's equation 1, and there's equation 2. This should be less effort. So we're just going to take this equation 2, and we're going to immediately sub equation 2 into equation 1. And since we're subbing for y, that means we must want to find x. Okay. So over here, we're going to say 6x minus 3 times 2x minus 4. And that's going to be equal to 12. All right, let's do some work. So we have 6x minus 3 times 2x, so minus 6x. Negative 3 times negative 4, so that's going to be plus 12, is equal to 12. Now, 6x minus 6x, well, that's 0x. And we got to bring the 12 over to the other side. So in this case, when we do that, we have 12 minus 12, which is 0. But 0 times anything is 0. Well, we end up with a situation of 0 is equal to 0. You know what? That is true, but it doesn't tell us anything about the variables. What we have here is a situation that is always true. Always true. So since this is always true and gave us no other information, what we can say here is that therefore there are infinite solutions. Well, if there are infinite solutions, that means that they must be the same line, and it also means that they're parallel. So we could say the lines, put a little comma there, the lines are parallel and coincident. Parallel and coincident. And that's it. That's what we learned today. We learned how to determine, just by looking at some equations or looking at a slope and a y-intercept, to know whether there's one solution, no solutions, or an infinite number of solutions. And that was it. So thank you.